Okay, good morning. This is the Applied Airplane Aerodynamics class. Um, we started the class since last week. We had some discussions and we watched some videos. I hope you still have those videos in mind. The bulk of the material in the slides are sourced from Anderson's Fundamentals of Aerodynamics and the text on aircraft performance and design by the same author. Yeah, as we discussed last week, applied aerodynamics just implies the application of aerodynamics in the evaluation of view configurations such as the aircraft, spacecraft, missiles, or whatever is designed to interact with an atmosphere. And it doesn't have to just be the Earth's atmosphere, it could be the atmosphere of another planet. So long as what you're talking about interacts with air, then applied aerodynamics is the domain in which we discuss its uh, aerodynamic characteristics. Um, so when you are trying to practically evaluate such aerodynamic characteristics, that is the domain of applied aerodynamics. And as you recall, from the videos we watched last week, the flow around such configurations are real flow. That is, they are viscous flow. They are not inviscid flow. Viscous flows, as you also should know, are flows where the actions of viscosity are uh, taken into account. That is, they are not neglected. An inviscid flow is one in which the fluid is assumed to have no viscosity, zero viscosity. So such a flow, which is an inviscid flow, would not have something like flow separation or wake formation and all of those interesting things that make viscous flow what it is. And then the non-dimensional aerodynamic coefficients of lift, drag, and moment are the primary language of application in external aerodynamics. And we also discuss the differences between external and internal aerodynamics. External aerodynamics just pertains to the study of the interaction of air around the external surface of a body, where you'll be interested in knowing the lift, the drag, and the moment of such a body. Internal aerodynamics pertains to the study of the interaction of air in the internal parts of a body, like the flow through an engine or through a pipe. All such kind of flows are internal aerodynamics, or the studies of flows in such kind of applications is the domain of internal aerodynamics. Now we are going further into the slides. We need to look at the boundary layer. You are already um, familiarized with this in the incompressible flow class. So this are just supposed to be um, a reminder. You recall that there's always some friction between two surfaces. Once there's a relative motion, when you rub your palm, you feel some heat. That's just because there's friction between your palms as you're making a relative motion between them. And this is also true for fluid flow. So different layers of the fluid, as the fluid is moving, will be rubbing against themselves, and then there's some friction. Yes, eventually friction within the fluid gives rise to the aerodynamic heating on the surface of the body that is interacting with the fluid. Then frictional shear stress exists at any point in a flow where there is velocity gradient. So velocity gradient just means that the rate of change of velocity with distance above some surface where you are interested in. Uh, so long as there is some variation of velocity, um, distance of interest, then there's going to be velocity gradient. And once you have velocity gradient, then there's going to be some shear stress. And that's from Newton's law of viscosity, where it just says that the shear stress is proportional to the velocity gradient, and the, the constant of proportionality is the constant of proportionality is just the viscosity of the fluid. So, from the previous slide, we saw that once, because of the friction between the different layers of the fluids, and also because of the no-slip condition on the surface of the the solid object. And no-slip condition, of course, means that the a layer of fluid that is directly adjacent to that surface assumes the velocity of that surface. So when that surface is not moving, then that means the velocity of the layer of fluid that is adjacent to that surface is going to be zero. So however, the rest of the fluid will be moving with the free stream velocity. That means the fluid must accelerate from zero velocity at the surface to the free stream velocity away from the surface. And so um, there is a region of the flow in which that kind of acceleration will have to take place, and that region of flow is the boundary layer, and that is all evident from the last slide. Now, it is in practice we just treat the layer of fluid that is away from the boundary layer, that is outside of the boundary layer, we treat it as an inviscid flow. That is, we assume that the flow is inviscid in that region, since the velocity gradient is nearly zero, that is negligible. So we just assume that that portion of the flow is inviscid, and then the portion of the flow within the boundary layer, of course, we assume it. We don't make any assumptions about that. We leave it as we leave it as a viscous flow. And in this region, of course, the dissipative effects are included. That is the thermal conduction, diffusion, mass diffusion, and all that. Those effects are viscous flow effects that are included in such region of the flow. And we have the velocity boundary layer and the thermal temperature uh, uh, thermal boundary layer. Velocity boundary layer, like I was saying, there's relation of um, velocity from zero at the surface to the free stream value away from the surface. So that gives rise to some velocity profile that is usually shaped like this. The wall shear stress is directly proportional to the velocity gradient at the wall. That is from Newton's law of viscosity. And also here, I'm wondering if there's a way to move this video thing. I can't move it. It would have been nice for me to move it around, but I can't move it. Anyways,
You have the slide.
hmm?
You have the slide.
Yeah,
You have
but,
the slide. I've seen it. I will still
but
send it.
it would be good if somebody watching the video and doesn't have the slides would be able to see every part of the slide. I'll try to see if I can move this video subsequently. Anyways, since you have the slides, let's just continue. You can look at your own slides to see whatever this video is obscuring. So in the temperature boundary layer or the thermal boundary layer, the temperature also varies from some value at the surface. The temperature at the surface will not really be zero, because there's going to be some the surface would be at some temperature anyways. So the layer of fluid that's directly adjacent to the body surface will also have the temperature of the surface. And so because of friction, it makes, like I was saying in the previous slide, when you rub your palms, you feel some heat because there's some uh, um, there's some dissipation of energy that leads to the heat energy that you feel. So the same way, when the fluid layers are rubbing against themselves, there's some heat generation which um, uh, rises the temperature. And so the temperature directly away from the surface um, uh, rises because of the viscous dissipation, and then eventually because the velocity gradient is reducing towards the edge of the velocity boundary layer, the viscous dissipation decreases, and so the temperature profile bulges out around this portion and then goes back to the free stream um, uh, temperature. So this is the kind of profile that you have in the thermal boundary layer. And also there's um, the rate of heating to the wall, that is the aerodynamic heating, Q dot W, is equal to the negative of K. K is the thermal conductivity of the fluid times the TDY, that is the rate of change of temperature with distance away from the surface. And that will have to also be evaluated at the surface. So the TDY, it just gives you the temperature gradient at the surface. That is the TDY at y equals 0 gives you the temperature gradient at the surface. Here the VDY at y equals 0 gives you the velocity gradient at the surface. So these are two equations that are very useful and which you are quite familiar with already. So we move to the next slide. I'm not able to move. For the velocity boundary layer, there are two kinds of boundary layers that we can have, or it can have two different kind of natures. Either the flow inside the boundary layer is laminar, where the streamlines are smooth and regular, and fluid elements move smoothly along those streamlines, or a turbulent flow inside that boundary layer, where there is just a random motion of the fluid elements as the flow progresses inside the boundary layer. So it, yes, the fluid elements move in a random, irregular, and tortuous fashion. This figure here is supposed to give you an idea of what laminar and turbulent flows look like. And this is um, the smoke coming out from a cigarette. It comes out, um, when you look at it, you see um, it's going out smoothly at first, and then at some point it becomes almost random, or very random actually. So the point where it changes to random motion is turbulent flow, and then this motion is the laminar flow part. So we want to consider the velocity profiles through.
Considering this this thing about turbulent and laminar,
Mm.
because of the place where the attachment is laminar, the and trimming is turbulent.
Are you saying when the flow are separated and it's
The turbulent.
yes, usually it's when it has separated, it becomes quite tortuous and it's going randomly. And so yeah, it's turbulent. But you can also have uh, turbulent flow within an attached boundary layer. So, anyways, when our discussion progresses, I think you'll be able to understand better about um, what you are saying is also correct. Yeah. So we look at the velocity profiles through a boundary layer as illustrated in this figure here. For the laminar boundary layer, the velocity profile is uh, usually looks like this. It's shallow, the gradient is shallow. For the turbulent boundary layer, the velocity profile is usually fuller and the gradient is very steep. And when I say shallow and steep, I want you to imagine that you are, I want you to imagine you are going down a staircase. A staircase, let's say this is the top portion of the staircase, and this is you going from here to here means you descending the staircase. This is very steep, right? Or this would be very steep and this would be shallow, right? So that's what I mean by this being shallow and this being steep. And because this is shallow and this is quite steep, the velocity gradient, that is you going from here to here, the rate of change of um, um, remember that this is velocity profile that we are looking at. The rate of change of velocity with distance away from the surface is less than the rate of change of velocity with distance for the turbulent flow. For instance, from zero velocity, you go to a value here. Let's say this is at this portion it is 10, and at this portion let's say it is 20 meters per second, and you are going from zero. So if you look at the change from zero velocity here to 10 for the laminar, for instance, and then at the same distance away, this is already like 20. So that means the rate of change of velocity with distance for the turbulent flow will be higher than for the laminar flow, and that is the velocity gradient. Because the velocity gradient is higher for turbulent flow and lower for laminar flow, and also because the velocity gradient is proportional to the shear stress. That is to show us that the shear stress in laminar boundary layer is less than the shear stress in the turbulent boundary layer. What I've just um, um, explained with the velocity gradient here shows to us that the velocity gradient for laminar flow is less than the velocity gradient for the turbulent flow. And because with Newton's law of viscosity, the velocity gradient is directly proportional to the shear stress. So that means the shear stress for laminar flow is less than the shear stress for turbulent flow. It follows just from understanding this figure and linking it to the velocity gradient, and also going from the velocity gradient to the shear stress. Um, so this same kind of trend also holds for the aerodynamic heating, because the temperature gradient for laminar flow inside the boundary layer is also less than the temperature gradient for the turbulent flow inside the boundary layer. And that means since the aerodynamic heating is directly proportional to the temperature gradient at the surface, it shows to us that the aerodynamic heating in the turbulent flow boundary layer is less than the aerodynamic heating in the in the turbulent boundary layer. So this slide just tries to give us an idea of the magnitudes and variations of some of the aerodynamic coefficients, and particularly the drag coefficient. So if you have a flat plate that is normal to the flow, and this is the Reynolds number here is the Reynolds number here is about the Reynolds number here is about 10 to the 7. That's about 10 million. So the flow comes, it stagnates at the surface and then goes around the edges, then separates at the edges into the wake. And the wake is quite large, so the drag coefficient it's around 2.0. Remember that the drag coefficient is a non-dimensional coefficient, so there is no unit there, so it's just 2.0. For a cylinder in the same at the same Reynolds number, the flow stays attached on the forward surface and then also uh, separates at some point away. The wake is still large, but not as large as the wake behind the flat plate. And so because the wake is not as large as that, the drag coefficient is less than for the flat plate. So for the cylinder at this condition, the drag coefficient is around 1.2. For an airfoil which is streamlined, it's streamlined because as you can see, the shape is elongated and the flow stays more attached to the surface of the airfoil and separates towards the trailing edge of the airfoil into a very thin wake. Because the wake is very thin, the overall drag of the airfoil also becomes very small, 0.12. And this is still at the same Reynolds number as the flat plate and the cylinder. We go to another figure here. The Reynolds number is still a million, but this is a cylinder, a smaller cylinder that is 10, 10 times smaller than the cylinder here. The wake is still large compared to the cylinder diameter, and so we can see that the drag coefficient is still unchanged, so it's still 1.2. For a cylinder about this size as the one in figure B. Huh? Yeah, it's about the same size. And it's the same, I think this is still 10 to the 7. That's like 10 million. The flow, the flow here you see is more attached to the surface of the cylinder. For instance, the separation point is at the back instead of at the front here. And because the separation point has moved to the back of the cylinder, the wake is smaller than here, and so you see the drag coefficient is also smaller than it is here. So we have a sense of the fact that the larger the wake, the higher the drag, and the thinner the wake, the lesser the drag. What can you say is the difference between these two, between this figure 1.39b and figure 1.39e? I've already told you that the separation point moved from the front to the back. So that's a difference. But what do you think is responsible for the separation point moving from the front to the back? What do you think is responsible for the separation point moving from the front to the back? Hmm? Yeah, both of these scenarios have viscous flows because you have the separation and you have the wake. But just guess, the flow is more attached here. That's why the separation is delayed, but it's not as it's less attached here, and that's why the separation is faster. Anyways, the flow inside the boundary layer here is laminar, and that's why the separation is faster. The flow inside the boundary layer here is turbulent, and that's why it's more attached and the separation is delayed. So that is one of the usefulness of a turbulent boundary layer. It's the flow inside the turbulent boundary layer has more energy. The fluids have more energy, and so they stay more readily attached to the surface and not affected by the adverse pressure gradients on, and when I say adverse pressure gradient, I mean the pressure is increasing in the flow direction. And so if the pressure is increasing in the flow direction, the tendency is for the fluid element to be retarded. It doesn't have enough energy to go from the front stagnation point all the way to the back. But for a turbulent boundary layer, the flow has that much energy to even travel faster than it has when it is in a laminar boundary layer. For a laminar boundary layer, it's going, but the pressure keeps increasing in the flow direction. And so at this point, the fluid elements are not as energetic as to be able to move further. So they just separate. But for turbulent boundary layer, they still have more energy to go against that pressure increase in the flow direction. And so they stay more attached to the surface before they eventually separate. And that gives rise to a thinner wake and less drag as compared to the fatter wake and higher drag in the laminar boundary layer. And that's to give us an idea of why one would want to have a turbulent boundary layer as opposed to a laminar boundary layer. If you are talking about, for instance, the aerodynamic heating and all that now, one might recall from the previous slide that we said um, when the aerodynamic heating in a turbulent boundary layer is more than in a laminar boundary layer. So if uh, we might just say that maybe we expect the aerodynamic heating in this scenario to be more than in this scenario because there's a turbulent boundary layer here and laminar boundary layer here. If what you are interested in is to decrease the aerodynamic heating, that is, we don't want as much heating to the surface, then one might say, oh, we prefer to have a laminar boundary layer than a turbulent boundary layer. So it depends on the application that we are interested in to inform us what kind of nature of flow we want inside the boundary layer. We saw, this is just to show us again, we saw a video where I made this figure from. The flow, a viscous flow is a real flow, and the flow comes, it stays attached on the body of the cylinder and then separates into a wake, and the wake, there are vortices that keep shedding. This is a test section of a wind tunnel in which the flow has been visualized with smoke. So please remember what we are talking about. So shortly before the break, we said on this slide where we are going to consider the case of the real flow over an airfall. But before that, we just recall from thin airfall theory that the lift coefficient is directly proportional to the angle of attack. And that's what the plot, the figure here says. The y-axis is lift coefficient and the x-axis is angle of attack in degrees. Starting off, and this is for NACA 001 airfall, which is a symmetric airfall. Starting from angle of attack equals 0, at angle of attack equals 0, there is no lift. But as soon as you are increasing the angle of attack, there is lift generated. And that's why it's proportional. We see that CL is proportional to the angle of attack. The higher the angle of attack, the higher the lift. So this straight line curve here is what you get from thin airfall theory. We just say CL is equal to 2 pi alpha. And that's quite intuitive. If you've ever stretched out your palm when you are in a moving car, you would have felt it too before. When you stretch out your palm and you do not incline it to the floor, you don't feel any force pushing your palm up. But as soon as you start putting, inclining it, that is, you are giving it some angle of attack, you start feeling some force. And the higher you, the more you incline your palm, the stronger the force that is pushing it up. That force that is pushing it up is just the lift. That's the same thing that is happening to the airport. If you never tried it before, the next time you are in a car, you should try it so that you have a feel of what we are talking about. And that is what has been plotted here for uh, again, this equation is from thin airfoil theory, and because thin airfoil theory is an implicit theory, that is, it doesn't take into account flow separation and all that, it's not able to predict what happens around this point. What happens around this point is a viscous phenomenon. This is due to flow separation on the airfoil surface and all that. And because the implicit theory cannot predict flow separation and everything, it's not able to capture uh, the whole story. So the points, these points on the figure are experimental data points. That is, some experiments in a low speed uh, wind tunnel was carried out on this same NACA 0012, where the angle of attack is varied and then the lift is measured, and then it's plotted on the same graph as where you have plotted the thin airfoil theory, and we see that there's a match. That is, that thin airfoil theory is able to predict the behavior of the airfoil um, in such a flow and for such angle of attacks that ensure that the flow stays attached on the surface.
So it's always the angle of attack more.
So angle of attack is just the angle between um, the the chord line, for instance, of the airflow and the incoming free stream flow. So when I say chord line, this is a chord line, for instance. So if the flow is coming straight ahead and the airfall is just the way it is, and the flow direction is directly parallel to the chord line, then the angle of attack is zero because there's no inclination between the chord line and the incoming flow. But as soon as you start pushing this thing up, that is, you are doing it like this. Before it was like this and the flow was just coming. Now I'm doing this, then I'm giving it some angle of attack. That is, I'm increasing the angle of inclination between its chord line and the free stream flow. Then, um, then that is angle of attack. And once I'm giving it some angle of attack, there will be some lift generated. And the higher the angle of attack, the higher the lift. Yes. So the higher the angle of attack, the higher the lift. Uh, but then the angle of attack does not uh, that the statement that the higher the angle of attack, the higher the lift does not stay true forever, because for the experimental point we see that at a point here the lift starts to decrease as the angle of attack is increasing, right? It doesn't increase anymore. So this point is called the stall point. Stall.
I don't understand.
Hmm?
I don't understand this.
You see the variation of the experimental points, right? When it gets here, when you increase the angle of attack further, is the lift increasing from, let's say, from this point and this point. So when you have increased the angle of attack from here to here, what has happened to the lift? I'm talking about this point here, this point, and this point. So when I say increase in angle of attack, I'm moving in this direction, right? So that means going from this point to this point is increasing the angle of attack. So, but as the lift increased, is the lift here higher than the lift here? So that's what I'm saying. That means at this point, the lift is no more increasing with angle of attack.
That means maybe the aircraft is right?
So at this point, just listen and get what I'm saying, right?
That means the aircraft design is like this,
Uh, just get what I'm saying, right? When you are increasing the angle of attack, you are increasing the lift. But I said that doesn't happen forever, right? Because it gets to a point you increase the angle of attack, but the lift will decrease. And that's what we are saying on this curve here. Before you are moving, as you are moving up, that is, you are increasing the angle of attack, the lift is increasing, right? So as you are going in this direction, the lift is also increasing. These are the experimental points. But when you get here, look, for instance, for the darker point, when you get here and you move in this direction again, this is the next point. The lift just drops, right? So that means increasing the angle of attack further from this point has not made the lift to increase, rather it has brought it down. So that means it gets to a point when as you are increasing the angle of attack, that upward force does not come anymore and it brings it down. So that point is what we call the stall point. If you practice it with your palm out the window sometimes, you see that as you are increasing it, it gets to a point when you do this, then your palm just falls because there is no more lift. The lift is no more there, and then your palm just falls. And that's the stall point. If that's what you are trying to say with the aircraft as well, with the aircraft, when you keep increasing the pitch angle, it gets to a point, it's it just starts falling because it's no more able to produce that lift. So that's the stall point. So the angle of attack at this point when the flow stalls is the stall angle of attack, the stall angle of attack, and then the CL, the coefficient of lift at that point is the CL max. Because that's the maximum CL that you can get to. The next thing is stall. So uh, the stall that we are talking about is as a result of flow separation. The flow was attached up to the point where um, uh, the increment in angle of attack was still increasing the lift. But as soon as we reach stall, the flow separates on the surface of the airfoil, and then the pressure difference that was making the lift to be generated is in the reverse direction, and then the lift is just lost, and then you stop. So that is as a result of flow separation. And like we said, in an inviscid flow, we don't have flow separation. Inviscid flow is only, sorry, flow separation is only present in a viscous flow. So that is why this CL equals to pi alpha, which is a result of an inviscid theory, which is the thin airfoil theory, is not able to predict this uh, uh, behavior here. That is why these points are not lying on this line here. So this is the real thing. The data points are the real thing, and then the line is just the theory, which is not able to predict the real thing at all. And that's just because this theory, is an implicit theory that is not taking into account the viscous nature of the flow. So we'll go to the next slide. So I've moved the video up so we can see this figure here. This is the airfoil. And this is the angle of attack, like I've just explained, is the angle between the chord line and the free stream direction. The higher you push up the angle of attack, as we saw here, the higher the lift. But the stall point, you have pushed it to the limit, and then the lift starts going down. And that is what we have seen here on this graph, that the higher you increase the angle of attack, the higher the lift up onto this point, where a further increment in angle of attack just leads to loss of lift. So that is what is happening here. And you see that it's almost abrupt. Like you get there and then you just fall. And that's why the pilots, when they are flying, they don't want to get to the stall point, because when you get to the stall point of the aircraft, most pilots cannot regain uh, control. They just start falling. So this is a leading edge stall. The stall is abrupt. The stall is abrupt. Huh? That's why they have a stall owner, that so when you are getting close to here, the store owner is telling you you are getting to that maximum thing. Don't increase your pitch angle any further, because once you increase it further, the flow separates totally from the surface of the aircraft, and then you just lose the lift. So that is what happens there. So that means this is the safe region. The linear portion of the graph is the safe region, where the lift is just proportional to the angle of attack. Or once you get to the stall region, that is the unsafe region. So this kind of behavior here is what we call leading edge stall, where the flow separates from the leading edge, and the separation just goes all the way to the trailing edge on the upper surface of the airport. So that's the first kind of stall that we are looking at. And if you look at its graph, we see that that thing is abrupt. Abrupt means it just goes. If you don't have a stall warner, then that means you think you are getting it, and then you increase it just a little bit more, then you just fall. So that's leading edge stall. The next kind of stall is the trailing edge stall. So all that we have talked about, the flow separation and all that, I hope you've been able to see that stall is just linked to the separation of flow on the surface of the airfoil. So stall is linked with the separation of flow on the surface of the airfoil. So for a trailing edge stall, the airfoil, as you keep increasing the angle of attack, the lift also keeps increasing, but then at some point, the flow separation starts from the trailing edge. So instead of the previous one where we saw that the flow separation started from the leading edge, and then it just fills the whole upper surface at once, for this one, the flow separation starts from the trailing edge, and then it doesn't go all the way to the leading edge, but it separates but doesn't go all the way, and you keep increasing the angle of attack further before the separation now travels up onto the trailing edge and fills all the upper surface of the airfoil, and then you eventually stop. So there's a gradual loss of lift, because as the flow starts separating, you start losing the lift bit by bit, or you start not making as much lift as you would expect before you eventually just lose the lift around this portion. So this is what we are trying to say for the trailing edge stall. The stall is softer, so it's not sharp, it's not abrupt, because the flow separation starts from the trailing edge and it moves gradually to the leading edge before there is eventual loss of all the lift. So this is what has caused this kind of softness in the stall. It's not abrupt. So obviously, if your aircraft has like a thick airflow, that means when you are going towards stall, it will not just fall. It will still, yes, there will be like a smooth progression to stall, and it just don't fall off like that. So that's the trailing edge stall,
So
and
the
this is
sharp story is for leading
when it's a leading edge stall, that's a sharp stall,
or
and then when it is trailing edge stall, it's a soft stall, and that's what we have here. You see a sharp stall, that's for leading edge stall, that's NACA 0012 for instance, and a soft stall is a trailing edge stall, which is this one that has been drawn here. And then there's a third category of stall, which is the thin airfall stall. That's on the next slide. The next category of stall is the thin airfall stall. And for this, this is a very good example of what can have the thin airfall stall, because this is just a flat plate. So the flow is there. As you are increasing the angle of attack, there is a separation here at the leading edge, but the separation doesn't go all the way to the back. It separates and then it reattaches at some point, and it goes there, but there's already some separation here. So that's what you are saying here. As you are increasing the angle of attack, there's a small separation point bubble. That separation bubble stays, but the rest of the flow stays attached to the trailing edge of the airflow. And then as you keep increasing the angle of attack, the separation bubble starts traveling, growing in length, in width and length, and then traveling to the trailing edge of the flat plate until you get to that point where that separation bubble has filled all the upper surface of the airfoil, and then you eventually just stop. So this kind of behavior ensures that the lift generated on the flat plate is not as much as for the other kind of airfoils that you have seen, and also, but because the trailing, the separation, there's a migration of the separation region as well. The stall is not abrupt, it's also a bit soft. That's why on the previous slide, if I try to go to the previous slide now, on the previous slide we saw that the graph shows a softness in the stall. So the variation of the CL max with the thickness of the airfoil. This has been plotted, so this is CL max on the y-axis, and this is the thickness of the airfoil on the x-axis. And this have been plotted for different Reynolds number there. So, but what we can see is that it's the CM max starts to increase as you increase the thickness of the airfoil, but it gets to some maximum and then starts to decrease. So that's the general variation of the variation of CL max with the thickness of the airfoil. And the reason why it gets to a maximum and then starts decreasing is just because of the flow separation. So flow separation is responsible for lift coefficients for the maximum value in the local maximum that we are seeing in the variation of lift coefficients with the airfoil thickness. And like we have shown before, it's flow separation is something that is just strictly viscous phenomenon. It's you don't have flow separation where you don't have viscosity. So in an inviscid flow, for instance, there is no flow separation because the fluid has been assumed to have no viscosity.
so how can we differentiate the pixel camber from the graph?
From this,
Yes.
from this, no, what we are just, maybe you can't see it well, but this graph just says airflow thickness on the x-axis. So thickness, not camber now. It's just, is it thin or is it fat? So that's what this is telling us now. When you are looking at your slide, you can zoom in more. Here, once I start recording, I don't have the luxury, or maybe I just don't know how to do it yet, to zoom in and zoom out and do all of those things. Uh, but the graph here says F4 thickness and CL max. So that means when you are going in this direction, it just means you are increasing the thickness of the F4, and we can see that as you are increasing the thickness, the CL max starts increasing, but then it gets to a maximum and then it starts decreasing afterwards. And it is just a result of flow separation, which is a viscous phenomenon. A viscous effect are always governed by the Reynolds number, and so obviously the CM max is sensitive to Reynolds number. So we see that, like I said, the graphs are for different Reynolds number. We see that when you change the Reynolds number, the CM max also changes. So going further, we need to look at the stall. No, the lift, we need to look at two things, the lift to drag ratio as well as the stall. We just try to read um, this snippet that I put on the slide. Um, so the simple generation of lift by an airfoil is not the prime consideration, it's design. When you have an airfoil, it's not just enough that it's providing lift. You need to also ensure some other thing about it, right? What's the other thing that we have to ensure? Exactly. We need to ensure that it is providing as much lift as possible, but as less drag as possible. Because if it's producing so much drag, that means we need so much thrust to overcome the drag. So that's not a good thing. So when you are designing an airfoil, you want it to have so much lift at with less drag. So give, um, it doesn't pay the designer if an airfoil produces so much lift but also so much drag. So that is why this lift to drag ratio comes into play. That means we want to see how much lift the airfoil is generating as compared to the drag that is generating. So an airfoil that has a high lift to drag ratio is a very good one as compared to one which has a low lift to drag ratio. If I say high lift to drag ratio, it just means that the drag is low compared to the lift, because lift to drag ratio is just the lift over drag. If it is high, it means the numerator is higher than the denominator, right? And if it is low, does that make sense?
Yeah, if it's low, the denominator is low, is higher than
Exactly, that means the drag is higher than the lift, right? So uh, so the lift to drag ratio, an airport that has high lift to drag ratio is then an efficient airport. It produces lift with a minimum drag. So the ratio is a measure of the aerodynamic efficiency of that airfoil. So we want to see how efficiently that airfoil is producing lift. Uh, the standard airfoils discussed in this chapter have high lift to drag ratios. They are much higher than that of a barn door. A barn door is just um, a door that you are put there for it to fly. Even though it may, as if, for instance, if I throw this now, maybe it will float for some time and then it will drop, right? That means it will also produce some lift, but the drag will be so much. So the efficiency is not so good. as much as that of an airfoil. So the lift to drag ratio for a complete flight vehicle has an important impact on its flight performance. If we are able to get there, the latter part of the semester we'll also see this, that a flight vehicle that has a high lift to drag ratio has a very good flight performance. Here it says the range of the vehicle is directly proportional to the lift to drag ratio. Then number two, the maximum lift coefficient, that is the CM max. It's an effective airfoil produces a high value of CM max. Much yeah. So an airfoil that is very good, you want it to keep um, to be able to get to so much high CM max before it stalls, right? That means you want to be able to keep increasing the angle of attack before it eventually stalls. Also, we need to make a consideration here uh, that the maximum CL max determines the stalling speed of a complete aircraft uh, in- using this equation. And this equation is just from the definition of coefficient of lift. What is the coefficient of lift again? The equation, from what you can remember. How do you non-dimensionalize lift? Lift coefficient. Hmm? Hmm? Is that we want to try to find a way to increase the CM max of the airfoil. Um, Last class, we are also discussing the fact that for a cambered airfoil, that's at zero angle of attack, there is going to be lift generated at zero angle of attack. Last class, we saw that for a symmetric airfoil, thank you. So this is not a symmetric airfoil because the shape on the surface is different from the shape on the upper surface is different from the shape on the lower surface. So there's some curvature of the airfoil, so it's not symmetric. So this kind of airfoil, if it's at zero angle of attack, that is, it's not inclined to the flow, there is still going to be some lift generated because the shape gives it, gives it the lift. It's the shape ensures that the pressure as the flow is going over it, the pressure distribution on the upper surface is different from the pressure distribution on the lower surface, and so there's going to be some lift generation. But if this is a symmetric airfoil where the shape is similar, there's not going to be any pressure difference imbalance when this is at zero angle of attack. So there is nothing that will make the lift to be generated, and that's why the curve will start from zero then. So that means for a symmetric airfoil, you need to then put some angle of attack just to make sure that the flow here will be different from the flow here, and so you have some lift generated. But for a cambered airfoil, which is this one is cambered because there is some curvature. Already at zero angle of attack, the shape makes it possible for the flow to be different. So you have the lift generated. So and that's the case for when you have the the curve having some lift generated at zero angle of attack. So if you want to increase the CM, and like we were saying, the higher you increase the angle of attack, the higher the lift. It keeps going up until you get to the point where it's just going to lose lift that stall. So if at that point you don't want it to lose the lift, you don't want it to stop, you have to use some high lift device. And one of those things is to put to increase the curvature of this aircraft airfoil. So what you can do is to make this trailing edge, make it detachable so that you can bend it more, and that's what we are showing here. When you bend it more, that means you can get more lift from the airfoil as you are putting it. And that's why you see on those aircraft, I don't know if you know if you has ever been on an aircraft, but you must have been able to observe it in movies anyways. Those things that they deploy, the pilot deploy them going down, those are flaps, and that's directly from uh, what we are learning here is just trying to get to increase the CM max of the wing so that the V stall, like I'm saying, the V stall um, is decreased and the aircraft is able to um, um, stop on time when the pilot is trying to land. For instance, when he's trying to land, he will also deploy the flap so that it will increase the CM max and then decrease the V stall. When he's trying to take off, he also does that because he wants to be able to carry much weight. So those are just the kind of remember that this class is applied aerodynamics, so we are applying the knowledge of aerodynamics. That's what we are saying. So that means one of the high lift devices that you can use is a trailing edge flap, where you make the trailing edge a hinged one that you can detach, and what it does is just to increase the curvature of the airfoil, that is increasing the camber. When you increase the camber, you increase the lift. You increase the lift. So for instance, here this curve, the thick line curve is for a symmetric airfoil. When you put when you make the the trailing edge, when you deploy the flap, it increases the CL, and that it moves the graph from where it is upwards. When you deploy the flap in that direction, it brings the curve from there to this one. Uh, but what we have to also note is that as you are increasing for instance, when you deploy it downwards and you've moved the graph from where it is here to this upper one, it also means that the angle of attack that you get to stall is decreased. For instance, before you use the flap, the angle of attack at stall is somewhere here. You trace it down, it's somewhere here. But when you engage the flap and you move the graph upwards, the angle of attack at stall moves backwards, and it's decreased. So that's just the downside to using a flap. Um, so going forward, the takeaway from this is one of the high lift devices is a trailing edge flap, and you use a trailing edge flap to increase the curvature of the airfoil so that you can increase the lift that it generates. And the reason why you want to have an increased lift generation may be because you want to decrease the V-stall. That is, when you are trying to land, you want to decrease the velocity of the aircraft, for instance, or when you are taking off, you want to be able to carry as much weight as possible by increasing CMAX at the same speed. Um, another another high device is a leading edge slat or droop or leading edge flap. So these are what we are saying. The leading edge is here, and this is the trailing edge. The first one we saw is a trailing edge flap, which you can deploy like this. And we said one of the downsides of using a trailing edge flap is that it decreases the angle of attack that you reach before there is stall. And the reason for stall, as we discussed in the last class, is due to flow separation. So that means if you want to keep going, if you want to increase the CL max for that, you can try to make the flow more attached to the surface. If you don't let it separate, then it can keep going up and up. And that is why you then put a leading edge slat, something like that, or a droop or a flap. Just when you deploy it, it makes the flow more attached, and then you can push this up and get more lift. So this is what here you can see the streamlines are shown here. When you deploy it, you can push the airflow further up before you have flow separation. So what it does on the graph is to push the CL max in that direction. So at this point, usually for normal aircraft now, most of the aircraft that you see, they will combine both leading edge device and then trailing edge device. So you see some slat of droop, whatever it is that they are using, and then some multi-stage uh, flaps. They are all just the same. What they are trying to do is just to increase the CL max